Good morning. Welcome to today's webcast, Analyzing Process Performance with Multi-Phase Instrumentation and Control. I'm Mike Rhodes, Managing Editor of Hydrocarbon Processing Magazine, and I'm your moderator today. Not all refineries are the same, and as such, the challenges with blending crude feedstocks vary between facilities. Fluctuation in crude supply can be beneficial. However, it can also bring significant operational challenges during the desalting process that can have an impact further downstream into other parts of the distillation unit. In this webinar, Tracerco will discuss the solutions available for process analysis and optimization and offer insights which will empower operators to make more informed decisions, be safer, and more productive. Joining us for today's event are Neil Murch, Business Development Manager, EMEA, and Eric Graham, Global Commercial Manager from Tracerco. Neil Murch is the Business Development Manager for the EMEA region within Tracerco. He is an instrumentation and control system professional with more than 17 years experience in the oil and gas, manufacturing, and automation industries. Eric Graham is the Global Commercial Manager for Tracerco's advanced range of nucleonic instrumentation. He is involved both commercially and operationally in the strategic growth of the business. Coupled with 8 years of experience in process diagnostics, Eric utilizes his process knowledge and understanding to offer a unique insight into instrumentation applications and design. Okay, just some general housekeeping notes before we get started. Following the presentation, we will have a short question and answer session. You can participate in the Q&A session by asking questions at any time during the presentation. Just type your question into the Q&A box located on the bottom left corner of your screen, then click the Submit button. You may enlarge the slide window at any time by clicking on the arrows on the top right corner of the slide area. The slides will advance automatically throughout the event. If you are experiencing problems with the program, please press the F5 on your keyboard to refresh the presentation. You can also visit the webcast help guide by clicking on the Help button below the slide window. Now let's get started. I'm going to turn it over to Neil.
All right, thank you, Michael, for the introductions. And hello, everyone. Good morning, good afternoon, and good evening, wherever you may find yourself today. I hope everyone's well and staying safe during these strange times. So just a brief overview of the agenda. I'll look at the principles of radiation, and then Eric will give you an introduction to our process diagnostic services and how this can enable insights into your process and complement our instrumentation offering. I will then continue with the profiler, discuss a case study, followed by a short summary, and then finish with the Q&A, which will be hosted by Michael. So for those that may not be aware of Tracerco, you probably want to know what we do. So we've built on more than 60 years of experience to provide a total solution in process analysis and optimization by creating ingenious ways to measure the difficult to measure, offering insights which empower you to make better informed decisions, be safer and more productive. Generally, as a business, we provide services such as reservoir characterization, fuel security and assurance programs, on-demand diagnostics, and instrumentation systems using radioisotopes. So before we get started, I think it's important that we understand some basic principles of radiation. So what is ionizing radiation? This is radiation that exists all around us all of the time, but there are different types of ionizing radiations which come from unstable isotopes, nuclear reactors, X-ray generators, and some which also is naturally occurring in the form of cosmic radiation from the sun. Ionizing radiation is the process in which an electron is given enough energy to break away from an atom. It exists on the far end of the electromagnetic spectrum, which is made up of different wavelengths, such as radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma. So for example, radio waves have the lowest energy or frequency and the longest wavelength, while gamma at the other end of the spectrum has the highest energy and shortest wavelength. All of these waves travel at the same speed in free space, which is the speed of light. In its simplest atom, is hydrogen. It has one electron orbiting a nucleus of one proton. Any atom which has one proton in its nucleus is a hydrogen atom. So therefore, hydrogen 2 is called deuterium, hydrogen 3 is tritium. However, while all their chemical properties are identical, their nuclear properties are quite different, as only tritium is radioactive. The activity of an isotope is simply a measure of how many atoms undergo radioactive decay per a unit of time. So the SI unit for measuring the rate of nuclear transformations is the becquerel. And this is defined as 1 radioactive disintegration per second. And the old unit for this was the Curie, in honor of Pierre and Marie Curie, who discovered radium and polonium. So how do we use this phenomenon in process applications? There are 3 main types of ionizing radiation. There's alpha, beta, and gamma. Alpha is a molecule made up of 2 protons and 2 neutrons. They don't travel very far in air and are stopped by a sheet of paper. This isn't particularly useful in any sort of process application. Beta is a particle, electron or positron. It's caused by beta decay and is a little bit more energetic than the alpha particle, although it won't travel through a thin sheet of foil. There are some applications where this can be used in the industry, but it's quite uncommon. And lastly is the gamma ray. This is more similar to X-ray, and it isn't stopped by anything. It's simply attenuated or reduced depending on the density or thickness of the material between the source and detector. So it's this attenuation that we measure when it comes to the products and services that we supply. By looking at the change in measured dose rate, we can determine many different process variables in our instrumentation systems. In its simplest form, we position a shielded source and detector on the vessel walls to measure the change between gas and liquid for bulk level applications. The size or activity of the source is calculated based on the vessel design, such as wall thickness, insulation, and the process contents. So this can be by means of an MDS service or a fixed instrument to look at bulk level or interfaces. But there are many variations on this depending on the application, which enable you to measure more than just bulk level interface and density, or a mix of all 3 for our more advanced instrumentation systems. So what are the main challenges that we see when talking to our customers? Opportunity crudes can be an attractive option for refiners looking to improve flexibility, operating margins, increase distillate yields, or convert high sulfur fuels into diesel and gasoline. But they're not all without their challenges and difficulties. So whether it be oil sands, shale, condensate, higher total acid number, or increased levels of elemental impurities and contaminants such as waxes, solids, iron, or vanadium, all of these characteristics can lead to processing issues. So the efficient removal of these impurities, along with salts and water from the crude feedstock, is imperative to maintain reliable operations, prevent unplanned shutdowns and outages, and reduce corrosion and fouling. So foremost of these challenges is to monitor and manage the position and quality of the process fluids within the vessel. So this includes emulsion, downstream of distillation, namely the desalter. So whether the process involves inline or intermediate blending, the use of accurate and reliable level or interface control devices in the desalter can reduce and in some cases eliminate process problems resulting from unwanted carryover or carry under. I'll now hand over to Eric, who will discuss our process diagnostic services in a little bit more detail.
Thank you, Neil. For those of you who are unaware of Tracerco's history, we originally started as a process diagnostics company. A few research engineers within Imperial Oil decided to utilize radioisotopes and radiation detectors to determine if we can identify what was occurring in the process while it was operational. Now, some of those technologies are utilized today in crude engineering and desalting in order to identify process upsets as well as mechanical problems that may exist inside of the equipment. Now, one of the technologies that we utilize quite often is neutron backscatter. Neutron backscatter is a very simple process that requires the utilization of a neutron emitting source. Now, this source is going to emit very fast neutrons. Now, right next to that source is going to be a radiation detector that can pick up the slow-moving neutrons. Now, those fast-moving neutrons, as Neil discussed earlier, can penetrate almost anything. Now, one thing that they cannot penetrate is a hydrogen atom, because the nucleus of that hydrogen atom tends to be very, very dense. So that fast-moving neutron gets bounced back. That's where the term backscatter comes from. And it can be detected by the radiation detector now. So as we place this on the side of a vessel, the fast-moving neutrons penetrate the vessel and interact with the process. By measuring the response, we can get a representation of the molecular weight of hydrogen on the other side of that wall. This gives us an indication of what the different process media is and can tell us where the different interface points are. So the areas where we tend to use this is on storage tanks, separators, desalters, and reboilers and exchangers in order to identify whether polymeric fouling or where different interface points are inside these vessels. Now, when it comes to distillation towers, we can utilize this to determine what the froth height is, as well as if there's backed up downcomers or where the bottoms level is in the tray, and even identify if we have buildup in the bottoms level as well. Now, another technology that we'll utilize is what we call the TrueScan. Now, this is actually gamma transmission completely through the vessel. We climb up to the top of the vessel, and we set up a temporary system of cables and pulleys, and we suspend the radioactive source and detector. And from the top tangent line all the way to the bottom, we take a measurement every 2 inches. We plot the data and we analyze it. And it gives us an image that looks like this. Now, what we're able to determine from this data is we're able to identify the froth height on every tray. We're able to determine what the liquid level is on chimney trays. We can see weeping, flooding, fouling, foaming, entrainment, corrosion, as well as where your bottoms level is, and many times we can see buildup on the bottom of the vessel as well. Now, for the next slide, we have a quick question for you, and this is a poll, and we would appreciate your participation. Do any of you have any operational or maintenance issues with your current existing instrumentation? I'll pause about 30 seconds to let y'all have a chance to answer the poll, and then we'll go over the poll results in the next slide. For those of you who participated, thank you very much. I'm going to go ahead and move the slide on to the next slide so we can take a look at the results. So right now, those of you who participated in the poll, it looks like about 50% of you are experiencing issues with your existing instrumentation. 30% are not, and about 19.5% do not have any instrumentation currently in the field. So moving on, I'm going to go ahead and hand back over to Neil. So Neil can go over some of the various options we have with Tracerco on assisting you with your desalter operations, what the benefits are, and some safety issues as well.
Thanks, Eric. I'll just remind everyone that if you have any questions relating to anything that we talk about today, the Q&A section remains open throughout the presentation, so please feel free to ask anything you like, and Eric and I will answer as much as we can at the end of the presentation. So in terms of conventional profiling, as it's called, multi-phase measurement began with multiple density detectors installed on the outside of the vessel wall. A string of sources, typically cesium-137, are on the inside in a dip pipe, allowing the radiation to penetrate through the process fluid and the vessel wall. This gave us the ability to profile the phases within the vessel to a reasonable degree of accuracy. Resolution is typically 6 inches, and installation costs can be quite high depending on brackets and cabling requirements and where the asset's positioned. And the systems are typically made up of between 6 and 8 detectors to cover critical interfaces such as below the electrostatic grid or the tricoque area, but they can be larger depending on process and design requirements. But one of the main things we need to be considerate of is radiation safety. So when we look at external systems, it's important to look at this. As previously mentioned, radiation from inside the vessel penetrates the process fluids and the vessel wall onto the detectors, measuring the change in radiation depending on the process fluid. So this goes back to the attenuation that I mentioned before. So the denser the material, the less radiation is measured. The lighter the material or the less dense the material, the more radiation is measured. So this example shows a dose rate plot in the oil phase using 7 cesium-137 sources of 1.11 gigabecquerels each. So typically, the higher the dose rate, the more accurate the system, although that's not always the case. But we need to follow the ICRP guidance, which is the International Commission on Radiation Protection, which limits dose rates to the human body to a maximum of 7.5 microsieverts per hour. When we introduce water into the measurement range, we can see the dose rate on the detector reduces as water is denser than oil. So it attenuates more of the radiation on the detectors, which you can see in the lower part of the graphic. When the interface is clean, this is easily distinguishable due to the density difference, and it's easy to measure. The challenge comes when emulsion or rag layers form, and it becomes harder for the system to differentiate between the two when it's a mix of those densities. So it's also important to note that the external detector systems can't perform with respect to high accuracy when the vessels are not flooded. So this requires reducing the activity of the sources that would normally be in air as to avoid high dose rates externally. And if the interface level increases, the activity is not sufficient enough to differentiate between the oil and water. So this causes problems with respect to system accuracy. So the result of a poorly designed system or gas being introduced causes the dose rate on the outside of the vessel to increase dramatically or very significantly. And this is because there is no process fluid attenuating the radiation from inside of the vessel. So from the example that we see here, we go from around 5 microsieverts to in excess of 400 microsieverts, which is 155% larger than the ICRP recommendation. When we come to look at Profiler, we listened to our customers' concerns and developed a method of eliminating the possibility of external dose rates by placing both the source and detector inside the vessel. So in doing this, it also enabled us to provide a system that is far more accurate with respect to vertical phase resolution, as it utilizes smaller detector elements and a much smaller energy isotope in the form of americium-241. So americium-241 is the same isotope that's used in a conventional household smoke detector, purely because of its low energy properties. So we can use this isotope as we no longer need a large amount of energy to penetrate the vessel wall, only enough to pass through the internal housing of the system. When we look at using low energy gamma for the profiler versus higher energy for external detector systems, we see that the profiler results in no additional dose to the surface of the vessel or for the external system. To work correctly, there must be a dose rate in oil so that the interfaces can be differentiated between. So in this comparison, to keep things the same, the activity of all of the sources, of which there's 7 in each systems, is 1.11 gigabecquerels, although the isotope is slightly different. So from the dose rate plot, we can see that there isn't any radiation present on the outside of the vessel with the internal profiler system, where it physically needs to be for the system to operate in the external type system. So on to more detail of the profiler. This is a single integrated bulk level multi-phase interface and density instrument that's suitable for nearly all separation processes. Inherent to its design and its industry-leading high-resolution output, which can be as low as 30 millimeters, enables precise interface positioning. So first installed in 1999 in the North Sea between the Scottish Codes and the fjords of Norway, we now have over 600 units installed in a variety of applications around the world. So since our first, all of those years ago, we've developed several different variants to suit a number of applications like subsea separation cells, high pressures and high temperature process applications, which enable us to provide our customers with solutions to some very unique challenges. So the profiler typically comprises of 2 or 3 dip pipes in an assembly installed into a vessel through a single nozzle. A narrow dip pipe holds a chain or a string of low energy gamma sources, which are americium-241, while the remaining dip pipes hold an array of Geiger-Müller gamma detectors. Typically, each source is directed using a collimated rod onto 2 detectors above and below the plane of the source. So this collimation reduces the number of gamma sources that we need to use. It stops the radiation in all the directions except where it's required, which is on the detector. And it also creates a continuous measurement range by directing the radiation beam up and down. So measuring the density change in this way allows us the most efficient operating conditions to be maintained, as well as monitoring the effectiveness of chemical additive and mud washing regimes, for example. So each profiler is designed and manufactured in accordance with the process condition that is measuring and also the vessel design criteria. As radioactive sources and detectors are installed in a dip pipe, they remain non-contact with the process, and this allows for full removal if required while the vessel remains in operation. So there is no need to depressurize or enter the vessel for maintenance purposes. We have a number of control system architectures available. In this example, it's our T229 control module, which we developed by building on our years of experience in conjunction with operators to give us 5 analog outputs that can be used for control and digital signals for DCS visualization, which I'll come on to shortly. So this single module contains our proprietary algorithms that convert the raw data from the field device to a usable operator information interface. The module is also EX rated, so it can be installed in the field if required, which saves sometimes valuable space in equipment or control rooms. So just as we discussed previously in relation to sizing shielded sources to penetrate the vessel wall and the process fluid for external measurements, this has a positive effect in shielding the profiler from external sources of radiation such as NDT. So as the instrument is internally mounted, there is no radiation measurable on the outside of the vessel of the profiler due to the low activity gamma sources that we use not having enough energy to penetrate the process fluids. So other than that we need for the measurement of the vessel wall, if vessel entry is required, there's an isolation handle that pulls the sources out of collimated alignment to shield them to enable safe entry to the vessel for cleaning or maintenance, for example. So on to visualization. So we hear a lot about data, especially with industrial Internet of Things and Industry 4.0. But as an industry, do we really understand the importance of data collection and analysis? Data is very important with respect to operation and process optimization, as it helps us to identify process problems, assess performance. It also informs decision making and can evaluate return on investment. So we want to present the information in a way that's easy to understand for the operators at the heart of the process with integration to your DCS. The information can be used to control asset performance in real time or analyze trends to overcome process challenges, which empowers you to make real data-driven decisions. In addition to the real-time monitoring, we also have data trending that can be performed over longer periods, for example, to evaluate the effectiveness of mud washing regimes or chemical selection and dosing management. We also offer services to further enhance the quality of the data from the profiler by analysing data dumps from clients through our Monte Carlo simulations to give recommendations on changes to settings and configurations of the instrumentation. So if we look more closely at desalting applications, we want to be able to overcome the challenges that I covered in the beginning of the presentation, like the inability to diversify with crude blending, eliminating unplanned trips or shutdowns, and of course, reduce corrosion. If we lack the control over our process, we risk running interfaces too high and cause overloading of electrostatic grid systems. So this can cause loss of coalescent ability, which results in a large amount of emulsion forming, leading to carryover, carry under, and ultimately loss of production. So our solution with the profiler is to overcome these challenges to enable safe, reliable, and accurate process control and efficient asset operation. So being able to monitor the process in real time enables enhanced operator confidence and increased unit reliability while having the potential to reduce operating costs. In this example, we examine the use of alternative demulsifying chemicals and dosing rates, which we can see the effect of that in real time. So benefits of the profiling system, we want to obviously be able to characterize and control real-time process conditions. So this enables us to give an enhanced understanding of process and data-driven decision-making, high-resolution measurement and improved control. We don't have any moving parts, so the system is virtually maintenance-free. We want to reduce operating costs by optimizing the use and effectiveness of chemicals and also reduce manual sampling. We want to reduce corrosion downstream by enhancing the control that the operator has to allow for more efficient salt removal. As I've mentioned, it's radiography resilient, and we also offer improved environmental compliance by reducing the carry under oil in the water stream by being able to monitor the precise interface elevations in real time. So coming onto the case study, we were approached by a refinery over a year ago now to help them understand and diagnose the root cause of various process issues in their crude distillation unit. During the turnaround, some significant damage was found within the various distillation towers, mainly involving corrosion and tray positioning. It was believed that the issues could have been caused by poorly performing desalters. So we worked with the refinery to carry out our process diagnostic techniques and services on the crude unit, including neutron backscatter. So as previously discussed by Eric, these techniques offer non-contact solutions that can be quickly deployed and used while the vessel is online to assess the various liquid levels and interfaces, as well as analyze process conditions to ascertain failure modes of the distillation tower damage. So what we want to see is a strong signal change between hydrogenous layers that are clearly defined, which means a nice clean interface. So it also indicates that the vessel's working as per its design condition. However, the actual results from the study indicated that there was in fact no clear oil-water interface. So the neutron backscatter scans were carried out on both desalter vessels in a parallel train on their previous running conditions. So additionally, as part of the study, we also scanned several operating conditions which included variations in crude blend and wash water rates to look at the effects of these on interface level. So it was clear from our findings that the existing interface transmitter was malfunctioning and not reporting the emulsion layer correctly, leading to exacerbated issues for the refinery. So following the analysis of the results and consultation with the client, the profiler was chosen to replace the existing desalter instrumentation into a single integrated interface control and monitoring device. So using gamma ray absorption to measure the process fluid density and position by the change in radiation intensity, the instrument provides an accurate measurement of process fluid distribution within the desalter, offering continuous high resolution images and control of each phase. So as part of the total system analysis that we carried out on the distillation unit, We also provided one of our Hyperion density gauges that was used in conjunction with flow and volume measurements on the crude feed line, and this was to monitor the density of blended crude charge as part of the refinery's ratio control optimization. With repeatable, accurate and reliable real-time process measurements, the profiler provided the client with the confidence to correctly control operating levels, which enhanced separation. So for real-time monitoring, we also provided our proprietary software, which is our measurement and control solution that is a readily made graphical user interface that provides clear insight into separation quality whilst enabling efficient operation and control of the instrument. So the display options available from the HMI provided the client with a window into the vessel, allowing the operators to visualize the process density distribution and utilize the diagnostic data that was available from the profiler system. The HMI offered easy access to the process and instrument status in real time, as well as trend data, which allowed adjustments to the process to be monitored and changed on the run, enabling decisions to be made faster, analysis a lot easier, and greater depth of optimization. So the instrument is now being fully integrated into the client's DCS. So originally when it was installed, it was a standalone piece of equipment and just used as for tertiary monitoring. So as well as the real-time data that I've discussed, we also have the capability of historical trending. So the trend data is normally available for up to 12 months through our system, or even longer if it's logged through your DCS. And this can be used to diagnose process problems or optimization by providing enhanced data insights. So we normally found that, like I mentioned before, that this is used for optimization of mud wash regimes or chemical dosing, or the effectiveness of demulsification chemicals. So just to summarize the case study, in the months subsequent to the installation of the profiler on the first stage desalter, a number of key and measurable benefits were realized that enhanced the unit's performance and reliability. But due to the industry-leading resolution of 30 millimeters, the client's confidence in the interface level was increased, which led to optimizing the interface for maximum wash water contact, reducing emulsion break and chemical dosing by 50%. In relation to their crude quality, the refiner noted a 44% reduction in BS&W and an improvement in their salt removal efficiency of the unit with a reduction in chlorides by approximately 50%. The demand on the atmospheric distillation tower preheat furnace was also reduced due to eliminating excess water in the dehydrated crude, which provided a more favourable approach temperature. This also had an impact on reducing corrosion of condensing overheads and towers from hydrochloric acid due to excess chlorides in the heated stream being removed more effectively before it hit the train. So coupled with the enhanced instrument accuracy and the unit having no process trips resulting from a lack of control or upset due to interface incursions on the lower grades, this equated to a throughput increase on the asset of around 20,000 barrels a day, which was quite significant in this case. So when we look at typical applications, the profiler can be used in almost any separation application where accurate control and monitoring of multiple process phases is required. We have profilers installed everywhere from subsea compression skids to desalters and HF alkylation units and pretty much everything in between. So it's a very versatile piece of equipment. And we have one more poll question just before we wrap up. So we'd like to know which measurement principles you're most likely to use for control of liquids and liquid level interfaces in your application. So again, we'll give sort of 20, 30 seconds to allow people just to answer, and then we'll review the poll question. All right, thank you to everyone that's answered the question. That's interesting. So half of our respondents that answered are looking at guided wave radar and about a similar proportion of nucleonic and capacitance. So hopefully we'll get some questions in the Q&A towards the end to try and clarify that a little bit further. And so that brings the end to today's webinar. Thank you for your attention. Please feel free to download our Insights through AR app through your app store, which enables you to interact with all of our equipment and system models in augmented reality in the comfort of your own home at the moment. And it also offers access to some more information on our products and services. So I'll now hand back to Michael to host the Q&A where Eric and I will answer all the questions you have. So thank you.
Sounds great. Thank you, Neil. We will now transition to the question and answer portion of our webcast. For our audience, you can continue to submit your questions in the Q&A box located on the bottom left corner of your screen. Let's get rolling here with our first question. Is there a limit of crude gravity / density to effectively control desalter interface levels, i.e., how does it handle very heavy crude blend operation?
Yeah, I'm happy to answer that one.
Neil,
so, yes.
I'm sorry, I've already answered it in there, but I'll go over it.
Okay.
In the profiler design, we currently utilize a very low energy isotope, as Neil had explained earlier. This very low energy isotope allows a greater variance between the recognized density of the crude oil and the water. So we can identify much, much heavier isotopes. Currently in desalting, the heaviest crude that we're seeing in desalting is 14 API gravity, and there is a very clear distinction between the oil and the water in that application.
Okay, I'll move on to another question here. You guys will probably be able to figure this out. It says sensitivity to high ambient temperature salinity. That's all it says there.
With regards to this one, the sensitivity of the equipment to the process conditions is going to be completely dependent upon the material of construction for the dip pipes or the wells. Since there is no process contact between the sources and the detectors in the process, the only contact is going to be with the wells. Therefore, we can manufacture those wells or dip pipes out of whatever material the process would require. Typically, it's going to match the material of construction of the vessel itself. Very good question, by the way.
Okay, here's another one for you. What are the sizes of the orifices along the probe? And two-part question, I guess. Were there any fouling issues?
Once again, this is very similar to the last question. Those orifices are collimators, and the collimators are utilized to direct the beam of radiation. They're inserted into the dip pipes or wells. So once again, there is no process contact. Therefore, there won't be any possibility for fouling up those orifices.
All right, questions are coming into our audience. Remember, you can continue to submit questions. Is it suitable for oil and urea adduction solution interface?
The principle behind the function of the profiler is density. So at each specific elevation, we measure the density of the process. Therefore, the limitation is based on whether or not there is a variance in the density of the two process media. If there is a variance in the density, the profiler will be able to recognize it. And then subsequently, we just need to ensure that whatever material we manufacture the dip pipes or wells is suitable for the process.
Okay, got another one that has come in for you. Can profiler systems be used for delayed coker foam level determination?
The issue that we will have with cokers has to do more with the temperature of the process. Electronics do not like to have those types of temperatures. So what we've actually done is we've developed a system very similar to the profiler that is fully external, where instead of having everything inserted with one-to-one pairing of the source and detector, we utilize larger isotopes so they can beam across the entire vessel, and we have a segmented detector system so that we can get a semblance of where the foam level is independent of the rest of the level. So it's not necessarily the profiler, but it is a very similar technology that will allow us to identify the information you're looking for.
Okay. Another question for you. Is it possible to maintain a level of emulsion?
Yes. Whether we're using the profiler or our neutron backscatter, we are able to identify the level of emulsion. Well, not so much the level of emulsion, as well as the interface points between the water, emulsion, and the oil. Originally, the profiler was designed to identify mud or sand interface, water, emulsion, oil, and foam.
Okay. Another question here. If the level profiler is inserted in the tank vessel, will the buildup interrupt the measurement? And continues to say, as you know, crude oil or emulsion is very sticky.
So when it comes to desalting or separation, we have very few applications where we tend to have buildup, mainly because in these applications there will be a temperature to increase the temperature of the oil, so it will tend to not become sticky. Now, there have been some applications upstream where what we've needed to do is we've needed to separate the source and detector, allowing a bigger span between the two so that the bridging doesn't occur, so we're able to identify the density between them.
Okay, here's another question that has come in. Does it require regular maintenance? Cleaning the probe then? That's what it says.
We haven't really run into a whole lot of situations where it requires regular maintenance. The situations where we've run into extremely high fouling service, typically in the tar sands, what we'll do many times is we'll install a water jet system that can be turned on while the instrument is in service to clean off any potential material that's building up.
Okay. Can the instruments, especially the profiler, be connected to a DCS wirelessly?
At this time, the profiler does not have wireless connectivity to the DCS. If it's something that is important and you feel is necessary for your process, we can definitely take a look at it and develop the technology.
Okay. Here's another one. You mentioned that profiler nuclear sources are encased, which allows them to be pulled out without taking the vessel offline. I can envision this easily with straight vertical tubes used in vertical vessels, but you've shown several pictures of horizontal vessels that have a curved profiler mount tube. Are these also able to just pull out without taking the vessel offline? When the sources are put back into the casing, how do we know they have returned to their exact same elevation and rotational orientation? Would you like me to read that one again? That's a pretty complex.
Yeah, there's a lot in that one.
Should I read it again for you?
Please.
Okay. You mentioned that profiler. You mentioned that profiler nuclear sources are encased, which allows them to be pulled out without taking the vessel offline. I can envision this easily with straight vertical tubes used in vertical vessels, but you've shown several pictures of horizontal vessels that have a curved profiler mount/tube. Are these also able to just pull out without taking the vessel online? When the sources are put back into the casing, how do we know they have returned to their exact same elevation and rotational orientation?
I'm going to go ahead and defer to Neil on that one. He said that he knows the answer to it, so I'll defer to him.
Yeah, I can answer that. Yeah, so the images we showed with the curved dip pipe on the horizontal separator were for a conventional external detector system. So to answer the question, yes, the sources in a curved dip pipe can be removed, but they're not typically collimated, which means they're just open to beam in any direction. So their level with respect to the detector and their rotation don't have an impact if they're removed and put back in. With the profiler, they're always in a straight vertical rod, and we have a post on the top of the instrument that attains alignment every time when the sources are removed. So whether we take them out and put them back in, they will always go back in the same orientation and position to make sure that we maintain the accuracy of the instrument and that the levels are always correct. So hopefully that answers the question.
Okay, well done. Here's another one. Can your system measure liquid slugs in natural gas pipelines?
Again, I'll answer that one. Yes, but we typically don't use the profiler in pipeline applications. We have other instruments that specifically measure density. So we would constantly monitor the gas density or the gas flow, and then when a liquid slug came past, we would register that change in signal. So we can do that as a single fixed instrument that just gives an indication, or we can combine it into two instruments into a system that gives you a slug monitor, if you like. So it'll give you time of flight and the estimated density of the slug. So it can be positioned further upstream, typically of the slug catcher. And as long as we know the distance, we know the velocity between both the detector trigger points, and then we can then tell you approximately how long it's going to take for that slug to enter the vessel.
Okay. Do you need to separate the source and detector in the separators involving heavy oil? Do you recommend using the external one for this application?
Yeah, again, I'll answer that. When we look at heavy oil applications, the accuracy of the system is a function of the amount of radiation that we measure. So we take the process information from the client and look at the densities of the process fluids and the delta between oil and water, for example, so that if the conventional or the standard americium type source that we use is not of sufficient activity, we can increase that, or we can use a cesium type isotope with an internal solution.
Okay, here's another one. Do you have any non-nuclear level profiler?
At this point in time, we don't currently have one, but we are developing a non-nuclear solution at this point in time. So if it is something that anyone is interested in, we would definitely appreciate your voice so that we can ensure we capture all of your needs in what we're developing.
Okay. Here's another one. What is the maximum thickness of vessels that permit you to read the liquid level?
Neil, I'll take that one.
Yeah, okay.
Oh, okay, go ahead, Neil.
All right, okay. Because we measure internally, the vessel wall thickness doesn't matter. So for conventional instrumentation where we have sources inside and detectors outside, it's very important to know the vessel wall thickness because that has an impact on the amount of radiation the detector measures. Obviously, the thicker the vessel wall, the less radiation the detector will measure, or the larger the activity of the source has to be to compensate for that. But because the profiler is inside and we fix the thickness of the pipe that the source and detector collimation sits in, the vessel wall thickness doesn't matter.
Okay. Has the profile probe been used for safeguarding applications? this is in relationship with its initial probability of failure?
I'm going to be honest. I answered it in the text, and I'm not 100% sure what's being asked, but the profiler's been independently tested by third parties and has shown to have a mean time before failure in excess of 20 years. This was required in order for us to gain approval for the subsea applications that we utilize it in, where the profiler is put into a separator on a sled and then dropped to the seafloor.
Okay. Yeah, I'll just add to that as well, just because we're a little confused about the question. So we do also have a SIL2 control system that we can supply with the profiler if it's to be used in a safety instrumented function. So the instrument itself, as Eric said, already has the third-party assessment for probability of failure on demand. And then we have a CIRA-certified piece of software and system architecture that meets the requirements of SIL2. Hopefully that answers the question.
Okay. Here's another question. Is the profiler suited to other applications as well as desalters?
Currently, the profiler is being utilized in separators, upstream, downstream, as well as subsea. We have it in alkylation systems, whether it be crude oil, whether it be HF, sulfuric, or various catalytic type of services. We have it in amine flash drums. It's used in flotation cells, primary separations vessels in the oil sands, as well as I'm sorry, I just lost my train of thought. Neil, can you think of any other applications?
Yeah, I'll just go to push the slide that we had before. So hopefully you can see there. I mean, as Eric said, hydrofluoric and sulfuric acid applications. Any production separator, whether it be a desalter or a free water knockout drum, slug catcher, or second stage separator, where you have more than two process fluids that are being gravity separated. Desalters, dehydrators, settling tanks, and then also subsea storage cells and caissons. So the applications are, I would say, endless, but obviously you need to have more than one process fluid to be able to monitor and control the interface, which is where the profiler really shines.
Okay, and here's another question. Do you provide any other measurement solutions such as that for level or density as well as interface?
Yeah, we provide a number of different solutions. So when Tracerco sort of first came to fruition, beyond the process diagnostics capability, our primary systems were external measurement devices to look at bulk liquid level in separators and storage tanks. And then from that, we've developed the technology to look at liquid-liquid or liquid-solid interface detectors, multi-interface detectors, which is the profiler that we've just discussed, and also density detectors. And then in addition to that, the density measurements, we can look at liquid and gas, and also slug monitoring systems. So yeah, we provide a wide array of process measurement solutions. So if there's anything specific, then please get in touch afterwards, and I'm happy to discuss in further detail.
Okay, I think we have time for one final question here. Do you offer an after-sales service for technical support?
Absolutely. We have numerous channels and avenues in which you can get that support. Currently now we are developing where through the utilization of cameras and different Wi-Fi applications, we can in effect offer complete service and support remotely from the UK, as well as our call centers and training programs, so that we can educate operators and I&E personnel on not just the maintenance, but also the interpretation of the data. We offer data analysis and predictive analysis studies to help better optimize the performance of the equipment. And we also have training courses for radiation safety officers, and support in the licensing and filing of the paperwork for the equipment.
Okay, sounds great. We want to thank to our audience for attending today's webcast. We would also like to extend a special thanks to Neil Murch and Eric Graham and to Tracerco for putting together this timely and informative presentation. Finally, an on-demand version of this webcast will be made available in the coming days and will be emailed to everyone. Again, thank you to Neil and Eric and Tracerco, and to our audience for joining us. Thank you and have a great day.
Thank you.